Picture translating a long sentence, word by word, where each word has to wait for the one before it. That was machine translation in 2017, powerful, but painfully sequential. Recurrent neural networks process language one step at a time, and that bottleneck limited how fast models could train and how well they could connect distant words. This paper, from a team at Google and collaborators, proposes something radical. Throw out recurrence entirely. Throw out convolutions too. Build a translation model using only attention. They call it the transformer, and it doesn't just match the state of the art, it beats it, while training in a fraction of the time. So, what is attention? Think of it as a lookup. You have a query, a question, and a set of keys paired with values. The query is compared against every key, and the values are blended together, weighted by how well each key matched. The transformer uses a specific form called scaled dot product attention. The query and key vectors are multiplied together. A dot product measures how aligned they are. That score gets divided by the square root of the key dimension, softmaxed into probabilities, and used to blend the values. Why divide by the square root of d sub k? Because when key dimensions get large, the dot products blow up in magnitude. That pushes the softmax into flat regions where gradients vanish and learning stalls. The scaling factor keeps the softmax in a healthy range. It's a small fix with a big effect on trainability. Now here's the leap. Instead of running attention once, the transformer runs it 8 times in parallel, with different learned projections of the queries, keys, and values. Each of these attention heads can specialize, picking up different linguistic patterns. Their outputs are concatenated and projected back down. This is multi-head attention, and it matters because a single attention head has to average everything together. Averaging blurs distinctions. With multiple heads, the model can attend to syntactic structure with one head, long-range dependencies with another, and coreference, like matching a pronoun to its noun, with a third. Different subspaces, different jobs. The full architecture stacks these attention layers into an encoder and a decoder, 6 layers each. The encoder reads the input sentence and builds rich representations. The decoder generates the translation one token at a time, attending both to what it has produced so far and to the encoder's output. Each layer wraps its subcomponents in residual connections and layer normalization, standard tricks that keep gradients flowing through deep stacks. The decoder adds one twist. Its self-attention is masked, so I can only attend to positions before it. This preserves the left-to-right generation order during training. But wait, if there's no recurrence and no convolution, how does the model know word order? Attention alone is permutation invariant. Shuffle the input, and you get the same output. The authors fixed this with positional encodings, sinusoidal waves at different frequencies, added directly to the input embeddings. Each position gets a unique fingerprint made of sines and cosines. Because these functions have a nice mathematical property, any shifted position can be written as a linear function of the original. The model can easily learn to attend by relative offsets. And unlike learned position embeddings, sinusoids can extrapolate to sequences longer than anything seen in training. So why is attention actually better than recurrence for this? The paper makes a clean argument based on 3 criteria: computation per layer, how much can run in parallel, and the path length between distant words. A recurrent layer needs n sequential steps to connect the first word to the last. A self-attention layer connects them in a single step. That constant path length is the whole game for long-range dependencies. When any word can talk directly to any other word in one hop, learning connections across a long sentence stops being a losing battle against vanishing gradients. And when sequence length is smaller than the representation dimension, which is typical for sentences, self-attention is actually faster per layer than recurrence too. The results are striking. On the WMT 2014 English to German task, the big transformer sets a new state-of-the-art. It beats the previous best by more than 2 BLU points, and that previous best was itself an ensemble of multiple models. All this while training in a fraction of the compute of competing systems. On English to French, the transformer sets a new single model state-of-the-art and does it in about 3.5 days on 8 GPS, less than a quarter of the training cost of the previous best. This is the real headline. Better results, dramatically less compute. The parallelism unlocked by removing recurrence pays off directly in training time. The paper's ablation study is worth pausing on. They vary the number of attention heads, the model dimensions, and the type of positional encoding. Two findings stand out. Single head attention is nearly a full BLU point worse than the best multi-head setting, but too many heads also hurts. And learned position embeddings perform almost identically to sinusoids, so the sinusoidal choice comes down to that extrapolation property, not raw accuracy. Translation is one thing, but does this architecture generalize? To find out, the authors apply the transformer to English constituency parsing, a very different task where the output is a tree structure, often much longer than the input. With almost no task-specific tuning, the transformer beats nearly every previously reported model. Even more telling, the attention visualizations in the appendix show individual heads learning interpretable behaviors on their own. One head resolves pronouns to their